Before we get into computing more iterated integrals, we're going to step back a little bit and do an estimation problem. In particular, we'll estimate the volume of the solid that lies below the surface, z equals 1 plus x squared plus 3y, and above the rectangle, r equals the interval 1, 2 by the interval 0, 3, both of those being closed intervals. The order of the intervals is alphabetical. So for the closed interval 1 to 2, that means that x goes from 1 to 2. And for the closed interval 0 to 3, that means y is going to go from 0 to 3. Further, we're told to use a Riemann sum with m and n equaling 2. M refers to the number of subintervals for x, and n refers to the number of subintervals for y. The Riemann sum looks like the sum as I goes from 1 to m of the sum as j goes from 1 to n of f of x ij star y ij star dA. Let's look at the region R. Here we have the rectangle that goes from 1 to 2 on the x-axis and 0 to 3 on the y-axis. And letting m equal 2 means we're going to split this into two vertical rectangles, and letting n equals 2 means we're going to split this into, well, 4, cutting both the width and the height in half. We can see here that delta x is equal to 1/2 and delta y is equal to 3/2. Therefore, delta area, delta A, is equal to 3/4. As far as our choices for xij star and yij star, we're actually given a bit of direction here. Part A, we're asked to use lower left corners. For the four rectangles we're looking at, the lower left corners are at 1, 0, 1.5, 0, 1, 3/2, and 1.5, 3/2. And I've used here some colors so that you can see what I'm indicating with the lower left corner of each of these subrectangles. Well, each of these corners is an ordered pair xy, and we need to know what the function value is for each of these ordered pairs. And so I'm going to set up a table here that has as inputs x and y and outputs 1 plus x squared plus 3y, the function that we're working with. The point 1, 0 maps to 2. The point 3/2, 0 maps to 13/4. 1, 3/2 maps to 13/2. And 3/2, 3/2 maps to 31/4. Our volume is then going to be approximated by the quantity of 2 plus 13/2 plus 13/4 plus 31/4 times 3/4, our delta x. The arithmetic is that volume is approximately 117/8, which equals 14.625. Part B asks us to use the midpoint rule. And that's exactly what it sounds like. We're going to use the point that's in the center of each of our sub-rectangles. For this one here, we would say that the volume is approximated by the quantity of f of 5/4, 3/4 plus f of 7/4, 3/4 plus f of 5/4, 9/4 f of 7/4, 9/4, all multiplied by 3/4 because delta x hasn't changed and delta y hasn't changed. I meant to say delta A hasn't changed. We're using the same function definition, and I will leave it to you to verify that we get that the volume is approximately 399/16, which turns out to be 23.4375. Next up, we have another problem we're also going to do without actually integrating. We're going to evaluate a double integral by first identifying it as the volume of a solid. We're looking at the double integral over r of the quantity of 2x plus 1 dA, where r is the set of ordered pairs xy such that x is between 0 and 2, and y is between 0 and 4. In order to envision this as the volume of a solid, it'll be good to graph the solid. I'm going to start though with, since the function that's the integrand is 2x plus 1, I'm going to look at the trace in the xz plane, imagining that integrand f of xy is z equals f of xy, which in this case becomes z is equal to 2x plus 1. That's a line that crosses the z-axis at 0, 1 and has a slope of 2. This will translate into R3 as a plane. So what we have is a rectangular bottom and then an angled plane for the top of our solid. Now I've drawn here a grid in the xy plane, or part of a grid, where x goes from 0 to 2 and y goes from 0 to 4. So there's our region R. And then we need to translate this line here in the xz plane is going to turn into a plane in R3. It intersects the z-axis where z is 1, and then has an upward slope of 2. Well, I've translated the portion of the line in the first quadrant of the xz plane into the beginning of the plane in R3. And by drawing another segment here out at y equals 4, now I can start to see this taking shape. So the solid we're talking about is this solid here. There are a couple of different ways we could go about this. The sides are in the shape of a trapezoid, so we could use a trapezoid with a trapezoid as a base, and we have a solid with a height of 4. Yeah, let's go ahead and do that. So our volume is equal to, well, we need the formula for the area of a trapezoid. It's going to be base 1, which is 1, plus base 2, which is 5, divided by 2, times the height of the trapezoid, which is 2, times the, we'll call it the length of the rectangular solid, which is 4. That gives us a volume of 24.